So I'm Mark Wilkinson. I'm the director of the DiRAC HPC facility. And so the short version of the talk, if you do want to leave or have to leave or go to sleep, is that co-design of HPC systems is important. It's a good idea, and it does work in terms of delivering more productive, scientifically and research productive HPC systems. And so what I'll do in this talk is introduce the various systems that we have within DiRAC and show you some of the science that we've been doing. So our approach, DiRAC's been going since 2009. We're a distributed HPC facility with installations at Cambridge, Durham, Edinburgh and Leicester. So I'll talk about them in detail in a minute. But we provide the HPC resources for the UK community in theoretical astrophysics, particle physics, cosmology and nuclear physics. And our approach to building our services has from the beginning been according to this process, and it's been talked about by others in the context of designing their services as well yesterday and today. So we start out with a science case, which is developed by the user community across STFC, and it's then sent out for peer review. So that's essentially saying the science that we want to do is world leading over the next few years. We then translate that into a technical case, which we also get peer reviewed, which is essentially saying to deliver this science, these are the kind of services that you would need. It's not at the level of the detailed specifications. That's also peer reviewed, and then we go through a long period of co-design with our industry partners to deliver the final systems. And that's what leads to the final service specifications of the systems that we build. So we've been through that process several times. We're currently waiting for the funding for DiRAC 3, and so we've been through the case, the process of writing the science case, the technical case, and we have our technical designs ready. So if anybody has any money they would like to spend in the next couple of weeks, please get in touch. So what the result of that is from the perspective of the DiRAC community is because we've got a range of different science cases, we have a range of different architectures. So we've got three services. On the left, you've got the extreme scaling system, which is hosted at EPCC. That's 2 petaflops, and that's supporting the largest scale lattice QCD, quantum chromodynamics, particle physics calculations. On the right, we have our other capability system, which is the memory-intensive service at Durham. And the key thing there, it supports cosmological simulations. So there are simulations that will scale to large numbers of cores, but only if there's enough RAM to support that and to keep the cores busy. Whereas the amount of RAM on the extreme scaling system doesn't have to be as large. And in between, we've got the data-intensive service, which is jointly hosted by Leicester and Cambridge. And that has a mix of architecture, so I'll talk about that and show some of the workflows that we cover. So I said that co-design works, so just there's lots of ways you can show that you're doing interesting things. This is probably the least interesting way of showing that we're doing interesting things, but I'll show it anyway. This is an analysis of our publications. So it's summarized in the bottom. We've got almost 1,000 papers which are based directly on DiRAC calculations, and a lot more that are based on derivatives of calculations done on DiRAC. Over 50,000 citations it is at this stage. And in 2015, we had the most cited paper in all of astronomy. And what you have in the graph is essentially showing, so each block of things, so there is showing papers submitted in a particular year. So you go from 2014 on the right, this is the 2017 papers, and the different colored bars show citations of those papers in subsequent years. So the point is essentially that the papers get a lot of citations, and those citations are sustained over several years, which means it's not just that we publish papers that people go, oh, that's interesting, and then they show it's wrong, and then it's forgotten about. Though, of course, some of the papers that are highly cited are wrong, and they get cited because they're examples of being wrong. I don't have statistics for how many of ours are like that. So now I'll go through each of the services and just talk about some of the science that we're doing with them. So at Edinburgh, we have the extreme scaling service, also called Tesseract. It's an HPE SGI system. And the stats are there. The key thing about it is, in terms of the co-design, is the interconnect. So it's an omnipath interconnect in a hypercube topology. And the reason for that, I'll explain now in the next few slides, is that it balances exactly the bandwidth on the network with the kind of calculations that are being done. So in case not everyone is a particle physicist in the audience, I'll have two slides which summarize particle physics, or certainly my understanding of particle physics, because I'm an astronomer. So particles, like the proton, are made up of smaller particles called quarks, and these are held together by strong interactions which are carried by gluons. And trying to understand the strong force is absolutely key to understanding what the standard model of particle physics, and to see what the physics beyond the standard model is. So what you do is, in colliders like the Large Hadron Collider, you smash hadrons together because you don't see quarks in isolation. So you smash hadrons together and you see what comes out, and the products that come out of these collisions, the masses of those products, the lifetimes of those products, and their decays into other particles are all clues to the internal structure of them. So what lattice QCD, lattice quantum chromodynamics, does is it tries to predict these masses ab initio. So it's very cool in terms of the calculation, because it's essentially taking fundamental equations of quantum mechanics, working them through, and then telling you the mass of the neutron should be this. And then you can go and measure the mass of the neutron and of many other particles. In terms of how that affects the actual underlying calculation, so this Peter Boyle has developed a code called the grid code for doing lattice QCD calculations. And what you have to do is you essentially have a 4D volume, so 3 space dimensions and 1 time dimension, and you're using a finite difference operator with an 8-point stencil. And when you work out how much, so in the diagram, the solid lines, I don't have a pointer, but the solid lines there, essentially that diagram wraps around this way and that way, so it turns into a torus, and it's a 4D torus. So when you work out in terms of the communication between the nodes, you find that about 1 over L, so if L is the dimension of the volume of the calculation, 1 over L of the data references come from off the node. And if you then work out what interconnect bandwidth you need to allow for that, it's the network bandwidth is related to the memory bandwidth, 1 over the scale of the calculation, multiplied by a reuse factor, which is the reuse of the stencil in caches. And so what you actually want to be able to do is distribute large numbers of data points over large numbers of cores. Large numbers of nodes, in a way that will be balanced so that your nodes always have plenty of work to do. So this was done for the tesseract system in collaboration with HPE, and the mapping of the problem, the calculation, to the network topology means that the scaling of it is extremely good. So what you've got here is the gigaflops that of actual scientific calculation that the nodes are doing. That's the y-axis. And on the x-axis, you've got it as a function of the number of nodes. The different colors just represent different volumes. So the key point is, as you go, so when you're on one node, you can get you don't have any inter-node communication. As you go to larger numbers of nodes, you do have a decrease in the gigaflops that you can get, because you have some communication, but it scales, it's an exact weak scaling result, which is very nice. You can just keep scaling that on to extremely large calculations. So you can do a bigger problem as the system gets bigger, and because the network bandwidth is set at the right, is set correctly, you're getting 76% wire speed in terms of use of all the links, but also you're getting this flat profile, so you're able to deliver the same efficiency, and your nodes are actually doing plenty of work all the way through. And that's why this system has been able to do calculations which are scientifically able to compete with things that are being done on Summit, because it's such a well-balanced system. At Durham, we have the memory-intensive system. Again, the details are summarized here. The two key features of it are the large amount of RAM. So the Cosmos 7, the most recent iteration of it, has a total of 230 terabytes of RAM, which essentially sets the scale of the largest calculation that can be done. And also a checkpointing volume, a 340 terabyte fast checkpointing volume. And I'll say a bit more about that in a moment. So the kind of calculations this was designed to support are this. So what you're looking at here, I don't know if we can dim the lights, but this is the evolution of the universe, of a small part of the universe to produce in the middle what will end up being a galaxy like our own galaxy, the Milky Way. So what you see in this simulation, it's just stars and gas, but actually there's also a huge amount of dark matter, and it's the dark matter is providing the gravity that drives all of this. The colors are telling you when the gas is heating up, so red, the gas is getting hotter. And the whole way the evolution of the universe works is small things collapse first under gravity, then they merge together to form larger things, and you end up at the end with a thing in the middle here, which is quite like the Milky Way. And just then, so that you know, we live in kind of about 2/3 of the way out in one of those spiral arms. And so this work was done using the Eagle code, which was developed by the team at Durham. And a lot of work has gone into modifying this code and developing the next generation cosmological simulation code called SWIFT. And that was done as part of an IPCC project with Intel. And so what SWIFT does is it takes the standard simulation codes for cosmology, and it's a complete redesign of it. So there's many different optimizations that have been added into it to allow it to be more efficient in terms of the performance on the systems that we have at the moment. The key one is task-based parallelism, so it's breaking the problem up into smaller pieces so that most of the cores are working most of the time. Whereas in the older versions and in codes like Gadget that are very widely used, a lot of the nodes are waiting for other calculations to happen. Because the big problem in a cosmological simulation, at the center of a galaxy like the Milky Way, the timescales, the physical timescales are seconds, minutes, or hours. Whereas at the edge of the Milky Way, the timescales are hundreds of millions of years. And if you're simulating the whole universe, which they also want to be able to do, then you're talking about billions of years. So the dynamic range in terms of timescales means that you may have something happening at the center of a galaxy on a timescale of a couple of hours that then has all the other nodes have to wait until that has happened before they can proceed with the calculation. So Swift gets around this by, or helps to get around that using task-based parallelism. So that's now being used to do the next generation of cosmological simulations. One calculation that's been done already using it is to look at planet collisions. This was a result that was published earlier this year. It was the largest ever calculation of a planetary collision, and it was trying to explain why the spin axis of Uranus has a strange alignment relative to its orbit around the Sun, and it has a surprisingly low temperature. And so on the left-hand side, you have the particles colored by what they are. So in the center, the dark gray is rock, then it's got ice as light gray, and the atmosphere of it is shown, the hydrogen and helium atmosphere is shown in light blue, and on the right you've got the temperature map. And so this was essentially a proof of concept to show that you could do really high resolution simulations of planetary collisions that would explain the properties of the planets in the solar system. One of the technical innovations on the memory-intensive system that's really having an impact on the science delivery is the checkpointing burst buffer that was added. So as I said earlier, it's about 340 terabytes. And the nice thing of this is, so when it was installed, it was the fastest file system in production in Europe. And it's delivering about 180 gigabytes a second read and write. And what that means is you can do checkpointing much more frequently if you want to, and that's useful in terms of the scientific analysis later. And you can do it at a lower cost in terms of core hours that are lost, which are wasted while you're waiting and doing the checkpointing. So just as an illustration, this shows how the power that you can save when you're able to do it faster. So if on the left-hand side, you've got, if you did a complete checkpoint once every 24 hours, on the right-hand side, it's if you did it once every hour. And just to set the scale, these calculations typically run for 3 months or so. So the bars then show how much electricity is being used effectively, and the different colors tell you about the speed. So the highest one is if you're only getting 30 gigabytes a second, and the smallest one is if you're getting 140 gigabytes a second. So that's a bit lower than we actually get. So there's a huge saving in terms of power, which is good because I have to find the funding to pay the electricity bill, so it's nice when something reduces the power. But in terms of the science delivery, it means that you can have more robust simulations. And so as we go forward to larger systems where there's going to be more failures, you want to be able to do checkpoints in minutes rather than in hours. So it used to take about 5 hours to do the checkpointing. Now it takes under 10 minutes. So I'll just skip the next one. Okay, so one of the other applications that was run on it, so earlier today there was a mention of using a large-scale system for a problem that's where individual simulations are not that big, but you have to do a lot of them. And so the discovery of gravitational waves was an example of that. So we were asked by one of our research groups, could they have a large amount of time? This was around the end of 2016, the end of 2015. Could they have a large amount of time for a project that they couldn't really tell us anything about, but it had to be done in the next 3 weeks? So we were able to give them a large chunk of time on the Durham system, and what they were running was many simulations of mergers of black holes so that they could develop the signals which are shown here. So gravitational waves were discovered, where the announcement was in 2016, about 100 years after they'd been predicted, and the red curve that you see there is the observed signal, and then the grey is the reconstructed theoretical ones. And so the idea was, the role of DiRAC in this was providing templates of simulated mergers so that they could then be done, matched with the observed ones. And this is a good example as well of where AI and HPC are coming together, because essentially this was a set of simulations which were done on an HPC cluster, but then it was an AI problem to actually work out what the parameters were as a result of that. On the Leicester system, so this is data intensive, this is designed around problems which don't scale well. And so the Leicester and Cambridge systems have a range of different architectures included in them. So as well as a large Skylake cluster, we've got a set of fat nodes, and we have a 6 terabyte Superdome Flex server as well. We also have an ARM system, which I won't talk about now, but that was covered. It's part of the Catalyst UK system that Simon talked about yesterday. And the kind of problems we work on the Leicester system are illustrated here. So these are 4 different simulations by Matthew Bate from Exeter. And just to say, so all of the access to DiRAC is controlled by peer review. So each of the services is not associated. There's some link scientifically with the local, the host, but there's an allocation panel run by the Research Council STFC, and so all applications go through that panel. And so I'll just start that again. What you're looking at here is 4 simulations of the same cloud of gas, but the amount of metal in the gas is different. So it varies from being very low, so the top left is extremely low, that's as in the early universe. The bottom right is is essentially more metal than the sun. So essentially that's the kind of star formation that we see now. And the idea here is to try and understand, how do stars form? So in all the other simulations, we have to put in assumptions about if you have this much gas and you wait this long, you will get this many stars. These simulations are actually following the hydrodynamics and radiation transfer of that problem to work out how many stars do you get. And so what you see is the number of stars, which are the things that end up shining at the end of the simulation. The number of stars is different in each case. And if you look in more detail, the number of stars which are in binary pairs orbiting each other is different, and the masses, the masses of the stars are different. So what we can do is try to reconstruct the history of the Milky Way in terms of looking at the stars that are here now. We can then use these kind of simulations to say if there are this many binary stars, this is the nature of the gas that they must have formed from. Another application on the data-intensive service, and this is using the SuperDome Flex, the very fat node, is to look at the detailed line list. So these are the spectral lines in the atmospheres of extrasolar planets. So this was used earlier this year, actually it was just published very recently, to underpin the first detection of water in the atmosphere of an extrasolar planet. So what this boils down to is a very dense matrix problem where you're trying to find more than half of the eigenvalues and eigenvectors of a dense matrix. So none of the usual approximations allow you to do that, so you have to do a very large-scale matrix calculation. So a lot of work's gone into this, both on the hardware side in terms of using the SuperDome to have a large shared memory footprint, but also on the software side, working with HPE and Intel in order to get the libraries to work effectively at this kind of scale. So we're talking about matrices that are 100. So currently about 100 to 200,000 by 200,000 entries, and the idea is to go up to 1 million by 1 million entries. And again, that may not sound large if you're talking about sparse matrices, but if you're talking about dense matrices, that's a very hard calculation. So finally, the data-intensive system at Cambridge. It's got several different types of architecture in it, so a mixture of Skylake, a KNL component, and some NVIDIA GPUs. It's a joint service between the Tier 2 for EPSRC, the local Cambridge resource, and DiRAC. And a part of the design there is the data accelerator, which topped the IO 500 in June earlier this year. So it's 0.5 petabyte of flash storage. And the idea of that was to be able to hold a large data set from some of the satellites that we're trying to model the data from, to be able to hold that in storage which could be very rapidly compared with simulations while they're running. And so one of the kind of cool things that they're doing there at the moment, so on the science side, is looking at the outflows of gas from galaxies. So in the earlier simulation, there were lots of bits where when I was showing the formation of the Milky Way, there were lots of periods where you kind of saw the gas turn red and expand, and that was when supernova explosions had happened. Now, another reason why gas gets shot out is there's a supermassive black hole at the center of a galaxy, and if you drop some gas onto that, you get a release of energy, and that can drive these kind of outflows. So they're driven out on very large scales. So essentially in this case, you're talking about a scale which is bigger than the entire Milky Way. So the Milky Way would be at the center. And that's what you're seeing there, is gas being driven out into a galaxy cluster. And what's really neat is we don't know exactly how these jets form, but there's a lot of work going on from the Cambridge group to try and understand how the jets are launched. So in this case, you start out, I'll start that again. So you have a disk of gas at the center of the galaxy with a supermassive black hole in the middle. The supermassive black hole is actually not aligned with the disk. So it's spinning, but the axis that it's spinning around is pointing into the disk. So when it initially when it starts, it launches a jet of material that plows into the disk, does a lot of damage. That's what you're seeing here, is various events. But at the end, you'll see the jet manages to escape. And you end up with a jet that looks very like the one in the previous simulation, pointing perpendicular to the disk. And so this is one of the first time that that process of understanding how it is that you get this jet launched from the scale of a very small region at the very center of a galaxy, but it ends up aligned, pointing perpendicular to the overall scale of the galaxy. So in the last couple of minutes, I'll just mention how this fits in with the larger scale picture that Mark mentioned in his talk yesterday. So we've done a lot of work over the last 18 months in terms of developing a roadmap for supercomputing on all different scales for UKRI. And in the white paper for supercomputing, the first recommendation was we should have a science case. So essentially the same process that many of us are using to develop our services, where you start from a science case, then you build a technical case, then you build your system. So my punishment for putting that as the first recommendation was I was then asked to go and edit a science case. So that's what we've been doing this year. And so by August, we had a document which has now gone out for peer review. It'll be the basis of business cases on all scales of supercomputing over the next few years. And we've covered the areas are shown here. Mark also mentioned them in his talk. I'm not going to talk in detail about them because most of them are kind of obvious. The one that, as been noted, is kind of new and growing is the digital humanities and social sciences, where there's a lot more data being gathered, and there's a huge opportunity there to do new calculations which will improve public policy. It'll improve governmental decision making, apparently. And there's a lot of things can be done if we can harness those data. So that's an area that will grow. But there's one I just want to pick up on, which is the mathematics and science of computation, because this was a theme that we deliberately included in the science case because it kind of underpins everything that is going on at the moment. So we said that there were various challenges, and it alludes to the need to support software and skills as well as just the hardware. But this idea of developing mathematics at scale, so actually working with mathematicians and computer scientists to make sure that we're developing the right algorithms, then looking at how the next generation of hardware is actually going to perform. So that's the point 2. The third one is then ensuring that the algorithms that are being developed and that will work on these new systems are also adopted by the communities. And that's not a trivial process. So it's all very well having really idealized algorithms available, but if they're not being taken up by the communities, it doesn't actually benefit us. Fourthly, working with industry to co-design. There's lots of examples of that over the last couple of days. A development cycle which essentially goes through that process multiple times. So we keep on ensuring that the systems that we're building are based on strong science drivers, but that we're also using the right algorithms to be able to take advantage of the hardware. The final point is probably UK specific, but I'm sure there's equivalents in other countries. Essentially, at the moment, it's very hard for this kind of work to get recognized because it doesn't get published in the right kind of journals. And so it's actually quite difficult, but important. If we want people to focus careers on doing this kind of work, we have to have a way that the quality and importance of what they're doing can be recognized. And so the final slide is just to note that in the context of the co-design part, which has obviously been the underpinning for all the work we're doing on DiRAC, and is now the basis of many other services as well, we recommended in the white paper that we needed a national technology horizon scanning program, which was actually funded so that we could go to industry partners, and rather than what we normally do, which is we don't have any money, can we have something free, we'd actually be able to go and say, well, we have a little bit of money, can we work together and co-design this particular type of hardware? So the idea is there will hopefully be funding available, and there's a small scale version of it will be starting quite soon. And this will allow us to have annual investments. So essentially we buy, test small deployments of all the different bits that we need to put the larger scale systems together, and then the software engineers and the community are able to take advantage of them. So my conclusion slide is very simple. I think better systems, we're all working very hard to deliver those, combined with better software and algorithms, so not just coding improvements, but actually fundamentally rewriting some of the algorithms that we're using, will lead to better science. It'll lead better science in terms both of we'll have services that can deliver more science, but also the science will be improved by being able to do things like uncertainty quantification, which is a growing area and is increasingly important in terms of applications. And this means we need more people involved in hardware and software co-design, but I think that's a good thing, and I think there's a lot of people getting very interested in this because of the scientific benefits. So I'll leave it there. Thank you.